Hello everybody, welcome. This is May 2023, paper 2, and it's from time zone 1. Okay, first mark is a 15-mark question. Let's have a read. The mean annual temperatures for Earth recorded at 50-year intervals are shown in the table. Tami creates a linear model for this data by finding the equation of the straight line passing through the points with coordinates 1708, 8.73, and 1958, 9.45. First question, part A, asks us to calculate the gradient of the straight line that passes through these 2 points. So we've got these 2 points right here. This is our data set, which relates year and temperature. So we have different years through time, and then the corresponding temperature at that given time. All right, calculate the gradient of the straight line that passes through these 2 points. Nice way to get started, I guess. Gradient formula, remember, is in your formula booklet, and I'll just bring that up right here. It should be under functions, so topic 2, and here we go, 2.1 gradient formula m, that's our slope, and then it's y2 minus y1 over x2 minus x1. Essentially change in y over change in x. So let's go back to the document, write that out, and calculate the gradient. So m, this is for part A, m is y2 minus y1 over x2 minus x1. Sometimes it's helpful, if you want, you can label these values. This is one coordinate pair, x1, y1, and this would be x2 and y2. After that, we can just go ahead and substitute. So y2 is 9.45 minus 8.73 over x2 is 1958 minus 1708. Okay, let's go ahead and calculate this. Just bring up the calculator screen. Here we go. And let's solve. Okay, let's get a fraction. 9.45 minus 8.73 over 1958 minus 1708. Okay, come back to the document. Actually, here we have 0.00288. Alright, so let's go back to the document and write this out. 0.00288, and that's already to 3 sig figs. Okay, part B. Part 1 of Part B asks us to interpret the meaning of the gradient in the context of the equation. So here is Part B. So we know that the slope of a line is given by change in y over change in x. And sometimes we write this as change in y over change in x. So more conventionally, if you've ever seen, let's say, just a coordinate grid, for example, with 2 variables. In this case, we know y. This y-axis right here, oops, look this back. This y-axis right here is degrees Celsius, and this x-axis right here is given by time. So if slope itself is just the rate of change, that is to say for one change in, let's say, 1 year, unit time, what is our increase in the y dimension? So if we're talking about change in y over change in x, our y-axis is temperature, and our x-axis is time. So what we have is we have change in temperature over change in time, or just in more plain language, we have change in temperature per unit time. So this would be change in degrees Celsius per year. State appropriate units for the gradient. So this would be part 2. Part 2, appropriate units. So if we're talking about, once again, change in y over change in x, we're talking about degrees Celsius per year. That would be fine for our units. So if we have 0.00288, what we actually have is 0.0288 degrees Celsius, degrees Celsius per year. And that's what this slope means, this gradient. We know that we change by just a small fraction of a degree every single year, according to our model. Alright, part C, find the equation of this line giving your answer in the form of y equals mx plus c. Alright, so we have a slope already. We have a value of m. Let's go ahead and write this out for c. We have an equation of a line which is equal to y equals mx plus c, and we already have m, so we have y is equal to 0.00288 x plus c, and we know mostly everything here. Well, we know our slope, but we don't know what the value of c is. We don't know our y-intercept in this case for an equation of a line, but we do have two sets of points. We have one point on the line, that is to say one xy value, and we have another xy value. So we can substitute either in and then solve for this unknown right here. So let's go ahead and do that. Let's take just the first value, I suppose, this one right here. So our y value is 8.73. 8.73 equals 0.00288, and we're going to substitute this y value right here, or sorry, this x value right here, this x value into our equation of 1708, and then now we can solve for the unknown. So now we've got an equation with just one unknown, and we can go ahead and use a little algebra if you want, or we can just solve this for c. Okay, so let's bring up the calculator and work this out. Let's go algebra, numerical solve. So let me get this up. Menu, algebra, numerical solve. 8.73 equals 0.00288. Open up a bracket, 1708. And we want to say plus c. We don't know what this is. And then, of course, ask the calculator what to solve for. There we go. So our value of c looks to be 3.81096. So let's go back to the calculator and write this out. So we know c is equal to 3.81 to 3 significant figures, and now we have an equation of a line. So that was this last missing piece of the puzzle. So let's go write that out. 3.81, that's our value of c. This is our equation of a line. Y is equal to 0.0288, our slope, plus our y-intercept, which we found by substituting. Okay. Use Tami's model to estimate the mean annual temperature in the year 2000. So the average temperature in the year 2000. So we've got this equation of a line right here. Whoops. We've got this equation of a line, this right here, and it relates inputs, so years, to a given temperature at that year, or the average temperature at that year. So let's go ahead and substitute this value of 2000 and see what the model would predict. So we have y is equal to, this is part D, y is equal to 0.00288x plus 3.81, and we know we're trying to predict temperature in the year 2000. There we go. So I'm actually just going to work this out on the calculator that I have beside me. That would give us a value. 288 times 2000 plus 3.81. And by our model, we would predict that it would be 9.57. And that's the value that the calculator gives, so no rounding required. Okay. For a question like this, you might want to see if it roughly corresponds with what we have already in our model. So we know 2008 is 9.76. This value of 9.57 degrees Celsius looks to be a pretty good prediction and might suggest that we're on the right track. Okay. Thandiso uses linear regression to obtain a model for the data. So really what we have, and often one of the challenges with paper 2 is interpreting what it's asking. So this question doesn't seem too bad, but when it's seen all at once as a 15-mark question, it's somewhat, or sometimes a little difficult to see what a question is asking. And in this case, the whole question can be broken down, at least I think, into two parts. That is to say, there's two individuals, Tami and Thamiso, trying to create a model to map, or to create an equation that maps a year to a given temperature, that relates these two variables. And Tami chooses 2 points on the line, finds the gradient, substitutes a point, and then she's kind of found this in kind of an arithmetic way, I guess, or you might say like kind of an old-fashioned way. And this is what her model predicts. And the second part of this question is Thandiso, and he's going to run a linear regression, and he's going to create a model using, in some sense, what's called a sum of least squares method. So he's going to use his calculator to solve this. And the question, I think, can be broken down that way. Alright, so Thandiso uses linear regression to obtain a model for the data. Find the equation of the regression line y on x. So this is part E. Find an equation of the regression line y on x. For this, we'll go into the calculator and use spreadsheets and run two-variable statistics. So let's go to the calculator and work that out. Alright, menu, spreadsheets, and we'll input the data that we have in our original table. So if we have x and y, x, this corresponds to our years. So 1708, 758, and these were just at 50-year intervals, 1958, 1908, 1958, 2008. And then we have the corresponding temperatures at those given times. So 8.73, 9.22, and so on. 13, 9.45, and 9.76. Alright, sometimes it's not a bad idea to check these over. 0.1, 12, 13, 45, 76. And these are all 50-year intervals. Okay. So after this, if we want to create a linear regression, we'll go Menu, Statistics, and we want to go Stat Calculations. And in this case, we have two variables. We're relating time and temperature. So two-variable statistics, tell the calculator where you put the x, where's the y. That's all we need to do for this. And then we can go down and, oh, I'm sorry, two-variable statistics is actually incorrect. What we want to do is run a linear regression. Here we go, linear regression, y equals mx plus b. There we go. Okay, so we're looking for those values once again of m and b, or what we called m and c earlier on, and here they are. So there's our value of our slope, and there's our y-intercept in this case. Okay, so let's go back to the document and write these out. So find an equation of a regression line y on x. We're going to have this equation of a line as y equals mx plus c or b, doesn't really matter. And let's use b since that's what our calculator has given us. And we have y is equal to, and just reading off from the calculator, we have m as 0.00, and it's given us 2557, so we'll round that to 2557, 256, x plus, and the value of b was 4.464, so we'll round that to 4.46. Okay. Find the value of r, the Pearson's product moment correlation coefficient. This is actually already given to us. So let's go back to the calculator screen. So we can do two-variable statistics, but this is actually given to us when we originally calculated a linear regression. And here it is. This is our r value right here. So let's go back to the document. Actually, here it is. Let's read it off. 0.8613. So going back to the document, r is equal to 0.861, three significant figures. Okay. Part F. Use Thandiso's model to estimate the mean annual temperature in the year 2000. So here we have F. So what does this model predict in the year 2000? So here's our equation of a line once again. 0.00256x plus 4.46. And now we have some input x. Let's substitute into this equation 0.00256, and then we'll put 2000 in here. We'll substitute in for x, and then we'll ask ourselves, what is the output, the temperature at that year? What would it predict? Okay, so that's more straightforward, kind of just calculations. I'm going to work it out on my calculator right here. 2000 plus 4.46. And this would give us a value, y is equal to 9.58. So 9.58 degrees Celsius. Okay, so not too bad of a question. Maybe interpreting what it's asking might be the challenge, but if you can get past that step, then perhaps not a bad question. All right. Thandiso uses his regression line to predict the year when the mean annual temperature will first exceed 15 degrees Celsius, so when it will first be larger than 15 degrees C. Part G asks us to state two reasons why Thandiso's prediction may not be valid. So let's write G right here. So two reasons why Thandiso's prediction might not be valid. First thing is, if he's trying to predict when it's 15 degrees Celsius, we see our model, its endpoint right here once again. It ends off at the year 2008, and it ends at temperature 9.76. And what Thandiso wants to do is he wants to predict when we might expect to reach this mean annual temperature of 15 degrees Celsius. So let's just write this out really quick. This is y, this is x, this was degrees Celsius, and this was time. And really what we have here is we have a set of values right here. And if we're looking at this, we usually have, what Thandiso is trying to do is he's trying to ask the question, what would the year be? What time would we have this temperature of all the way up here of 15 degrees Celsius? And the problem is that anything beyond this interval that we've collected data within, anything beyond this point is now called extrapolation. So this is something that would not be legitimate. This is extrapolation. Anything beyond our data set, any value, if we're trying to make a prediction beyond this, is extrapolation. Why is that? Because we don't know if the data is going to continue and it's linear, or we don't know if it reaches some kind of asymptote, for example, and it just tapers off. So it's not legitimate. We have what's called extrapolation. There's no guarantee that this trend will continue. So one reason would be extrapolation. That's why it would not be justified. The other reason is a little more complex, actually. What Thandiso is trying to do is he's trying to relate a y value right here, this 15 degrees, to an x value. So he's trying to relate an output to an input. And when we use a regression line to calculate or make a prediction, what we often do is we would use an input to map to some output. And there's no guarantee that we can necessarily go the other way. That is to say, we can start at our output and go to our input. So how could we potentially write that out? Cannot always reliably make a prediction from y to x. You might say cannot predict reliably from y to x, or from output to input potentially. That would be the second reason. Alright everybody, I hope that was helpful, and as always, best of luck. Take care.